ശരിയാണല്ലേ? ആ, എന്നാ എനിക്ക് ജസ്റ്റ് എന്റെ വീഡിയോയും നിങ്ങളുടെ KCB ഹോസ്റ്റ് KCB എന്റെ പേര് അടിയിൽ ഒരു സിമ്പിൾ മാത്രം സർവീസേഷൻ വെക്കാൻ നിങ്ങൾ ആ സ്ക്രീനിൽ കാണുന്നില്ലേ? എനിക്ക് അത്ര തന്നെ കാണും. സ്ക്രീൻ ഷെയർ ചെയ്തേക്കല്ലേ? അത് തന്നെ എനിക്ക് കാണാം. ഒരു സെക്കൻഡ് പഠിച്ചു. ഈ സ്ക്രീൻ കാണുന്നുണ്ടോ? അത് തന്നെ കാണും. ആ അതന്നെ കാണുന്നുണ്ട്. ആ മെസ്സേജ്.
ഹലോ ഹലോ
ആ
ഹലോ കുഞ്ഞുണ്ണി
സാറേ കേക്കാം
ഓക്കെ ഞാൻ കുഞ്ഞിനെ ഇല്ലേന്ന് അറിയാൻ വേണ്ടി ചോദിച്ചതാ.
ഉണ്ട് സാറേ, നമ്മുടെ ഫാക്കൽറ്റി ജോയിൻ ചെയ്തിട്ടുണ്ട്.
കണ്ടു, ഷെയർ ചെയ്യുന്നുണ്ട് ഇപ്പൊ.
അതെ സ്ക്രീൻ കാണാമല്ലോ അല്ലേ?
കാണുന്നുണ്ട്. ഓക്കെ, നമസ്കാരം. ഓക്കെ, അപ്പൊ നമുക്ക് ഏഴരയ്ക്ക് തന്നെ തുടങ്ങാം. നമസ്കാരം. ഗുഡ് ആഫ്റ്റർനൂൺ. ഓക്കെ, അനു എവിടെന്നാ ജോയിൻ ചെയ്തിരിക്കണേ?
ഞാന് കോയമ്പത്തൂരിൽ നിന്ന്. ഇവിടുന്ന് ലാപ്ടോപ്പിലാണ്.
കോയമ്പത്തൂരിൽ നിന്നാണ്.
കോയമ്പത്തൂർ.
ഓക്കെ ആയിക്കോട്ടെ. ഓക്കെ, അപ്പൊ കുഞ്ഞുണ്ണി 7:30 ആവുമ്പോഴേ കുഞ്ഞുണ്ണി ഒരു സ്വാഗതം പറഞ്ഞിട്ട് സ്റ്റാർട്ട് ചെയ്തോ.
ഓക്കെ സാർ. ഓക്കെ
അപ്പൊ നമ്മൾ നോക്കാം. ശരി എന്നാ. ഓക്കെ. സ്മൃതി ലൈനിലുണ്ടോ?
സാറേ
ഹലോ സ്മൃതി, 6-ാം തീയതി നിങ്ങളുടെ കണ്ണൂർ മീറ്റിംഗ് വെച്ചിട്ടുണ്ട് കേട്ടോ സ്മൃതി.
അതെ സാർ.
അപ്പൊ എല്ലാവരോടൊന്നും പറഞ്ഞോളാം അന്ന് ജോയിൻ ചെയ്യാനായിട്ട് മീറ്റിങ്ങിന്.
സാറേ.
അപ്പൊ എല്ലാവരും ആ സീനിയർ ആൾക്കാരെയും കൂടി അറിയിച്ചോളാം.
അവരോട് അറിയിക്കാം.
അവരെന്നെ അറിയിച്ചോളൂ. അപ്പൊ യൂണിറ്റിലെ എല്ലാവരും തന്നെ ആ മീറ്റിംഗിൽ ഒന്ന് പങ്കെടുക്കാനായിട്ടേ ഒന്ന് ശ്രദ്ധിക്കണം. എല്ലാവരോടൊന്ന് പറഞ്ഞിട്ടേ. അപ്പൊ ഇപ്പൊ അവിടെ സിയും ഡെപ്യൂട്ടിമാരൊക്കെ ആയിട്ട് ആൾക്കാരുണ്ട്. അപ്പൊ എല്ലാവരോടും ഒന്ന് പറഞ്ഞോളൂ. ശരി, ഓക്കെ. അത് പറയാൻ വിളിച്ചതാ. ഓക്കെ. ശരി, ഓക്കെ.
ഹലോ ജോബ് സാറേ, കേൾക്കാമോ?
ഹലോ, കുഞ്ഞിനി സ്റ്റാർട്ട് ചെയ്തോ?
നമുക്ക് സ്റ്റാർട്ട് ചെയ്യാം.
ബാക്കിയുള്ളവർ ജോയിൻ ചെയ്യുന്നു വിചാരിക്കാം. 13 ആളായിട്ടുണ്ടല്ലോ. വേണമെങ്കിൽ ഒരു 2 മിനിറ്റ് കൂടി വെയിറ്റ് ചെയ്തോ. 7:30-ക്ക് സ്റ്റാർട്ട് ചെയ്തോ.
ഓക്കെ,
നമ്മൾ 7:30-ആണല്ലോ സമയം പറഞ്ഞേക്കുന്നത്.
ഓക്കെ,
7:30-ക്ക് സ്റ്റാർട്ട് ചെയ്തോ.
ഓക്കെ.
ഓക്കെ. കുഞ്ഞുണ്ണി
സാറേ
സ്റ്റാർട്ട് ആക്കി.
ഓക്കെ. Respected President Job Sir, respected Secretary Sunil Sir, today KSEB Engineers Association is conducting its 30th webinar series program on microgrids. As everyone know, smart grids are the modern trends in electrical engineering. We all know that the central government has launched the smart city programs. It is being currently run in about 13 cities. And the evolution of smart grids is also a part of the smart city project. So on this topic today we got the engineer Er.Anu Kumar, assistant professor, Department of Electrical and Electronics Engineering, Amrita School of Engineering, Coimbatore, to take a small session on the introduction of smart grids and how it is going to evolve. Before we start the session, let me give a small intro about engineer Er.Anu Kumar. He received his BTech in Electrical and Electronics Engineering from College of Engineering, Trivandrum, India, and MTech in Power Systems from National Institute of Technology. 2007 to 2009, he served as Electrical Utility Engineer in the ITC Limited Bangalore factory. Since 2012, he is working as faculty in the Department of Electrical and Electronics Engineering at Amrita Vishwavidyapeetham, Coimbatore, where he is currently pursuing his PhD in Electrical Engineering. He has published research papers in various international journal conferences. His research interests include power quality in power systems, electric vehicles, and microgrids operation and control. On behalf of all the participants and behalf of KSEB Engineers Association, I welcome you, sir, for taking the session. Let me hand the session to you, sir. You can continue.
Good evening. First of all, let me take this opportunity to thank Kerala State Electricity this event for giving me the opportunity to share my views on smart grid and its evolution from microgrids to multi-microgrids. So we will straight away go to the session. So our topic is evolution of smart grid from microgrids to multi-microgrids. So to begin with, have a personal reflection of my association with KSEB. During my BTech times, we used to go to industrial visits to KSEB. And in 2017, in fact, when the central government launched the Power for All program, where the entire country was being electrified, we, few faculties and a set of batch of students, got this opportunity to visit a tribal village in Idiki, where we laid wires to many homes. And since more than 70 years, there were many villages which were not electrified. So it was a very heartening and a humbling experience we had along with KSEB engineers and personals when we electrified these villages and the lamp was lit for the first time. So this was a very good association which we had. And it was a part of the Living Labs village project where we, from our college, we send villages students. And in fact, recently we got a UNESCO chair for experiential learning, where we send students to villages to solve technical, electrical, and other challenges faced by the villages. So with this, I would wish to enter into the session, main session. So first we will discuss about the present scenario, and in the past decade, there were very drastic transformations and drastic changes in our happened in our sector as such. Okay, so let us start with renewable energy. This is known to most of us. Let us evaluate these transformations from various metric point of view, from various authoritative sources. So start with International Energy Agency. It is one of the very authoritative and reliable source of information related to energy sector, especially the renewable sector. And yeah, so
minute,
they
so
predict. Yeah,
can you just make
sure.
your presentation full screen, sir?
It is actually full screen.
Okay, I'm able to view a desktop actually. I'm able to view a desktop actually, and there is a small.
Let me just do it once again. Full screen mode.
Okay.
Yeah.
Yeah, now it's okay. Thank you.
So yeah, so they say, International Energy Agency, they say that electricity sector in the world is witnessing its most drastic transformation since its birth more than a century ago. This is what in their World Energy Outlook 2018 they have said. Now let us try to see what this drastic transformation is all about. Maybe we can look at it from an Indian perspective, from an Indian point of view. So there are some commendable and happy news from the Indian power sector as well. In fact, in 2018, this is again as per International Energy Agency, among the world nations, India was positioned 5th in the total PV installed capacity, and in 2000 we stood 2nd in the total added capacity, next only to China. So these were very good improvements from our nation point of view. And very recently, in the last November, in fact, India's renewable energy capacity became the 4th largest in the world. Okay, and this is in line with India's commitment in the Paris Climate Summit, where we had committed that we would go by 40% of our installed capacity will be renewables by 2022. And another good news to share is that if things go at this stage, it is predicted that India would very much its Paris commitment of renewable energy installed capacity of 2022. So moving forward, there are more things are happening in the sector, and why this is relevant in the smart grid context, because the future smart grid with all its information technology and communication technology is going to operate in the world of renewables. So it is very much imperative to have a good clarity to understand that from what exactly will be the power system scenario with the advent of renewables, and that would define the objective statement for all the upcoming technologies, right? And I also wish to convey that this session will be taking I will be taking power system perspective, the smart grid and the smart grid and okay. All right. So going further, actually echo is coming.
So now it's okay, sir.
Now it's okay, fine. So to add further, there is another very great news for India. Is that India's, as per Reuters and as per the analysis by consultancy Wood Mackenzie, India's renewable energy cost is the lowest in Asia Pacific, which is a great news, especially in the case of solar. This is the first good news. The second good news, which most of you would be knowing, is that it has now become cheaper than the cheapest fossil fuel-based power plant, which is coal-based power plant. In fact, renewables are now 14% cheaper than coal-fired power plant. So this means that we do not need, along with the climate change motivation for our pursuit towards renewables, now the economic motivation has also come, right? For the business point of view also, renewable is going to be more profitable. In fact, I just want to define the term levelized cost of electricity. It is expressed in rupees per kilowatt hour. So it is the rupees we have to pay for 1 kilowatt hour electricity from a given supply source. Yes, proceeding further. Another further good news for India, it is that India is blessed with a lot of solar energy. We have the equator passing through our country, so we are blessed with a lot of solar potential. To put the statistics into the discussion, according to Ministry of Statistics, as per our Energy Statistics 2018, it says that we have a total renewable power generation potential of 1,000 gigawatt capacity, right? 1,000 gigawatt. Of it, solar is around 649, and wind is around 302. Which together they are taking around 94% of the total potential. Quite, unsurprisingly, had gone for 175 gigawatt of renewable energy added capacity by 2022, with 100 gigawatts of solar, and if I remember correctly, 60 gigawatts of wind. So, and in fact, the demand is somewhat slightly more than 300 gigawatt, which makes the prospects very attractive because we have a potential which is more than 3 times our present demand. So, which is a really good and encouraging news for our country. So with I would also wish to add that the recent Saura project by KSEB and recent subsidies of up to 40% being given by the MNRE, Ministry of New and Renewable Energy, for rooftop solar. They are predominantly now focusing on rooftop solars. So within a very short time, the rooftop solars are going to be a very commonplace in our country, especially in Kerala, along with the very attractive Kerala model, which actually the one fundamental challenge for rooftop installation was identified by all consultants, that the upfront cost or the installation cost is high, and the beautiful Kerala model brings in this wonderful opportunity for consumers with a low upfront cost. Consumers of all slabs, in fact, with low upfront cost, they can go have a solar panel powering their home with low investment. So, considering these factors, International Energy Agency again proclaims that our system in India will see an unprecedented change in the next few decades. And amongst this will be the development of large number of microgrids in India. So our generation but surely, in fact, very swiftly moving towards from centralized generation to distributed generation, which we are blessed with lot of solar power. We receive more solar power than Western nations who install a lot of solar panels like Germany. We have much more solar power than them. But one of the challenges that one is its intermittency, it is stochastic. And second is that it's non-dispatchable non-dispatchability. So we have been following the conventional grid had been following this philosophy of supply following the demand. So whenever demand increases, let's increase the supply. We can increase the power supply by a hydropower plant and all that. But the future power grid or the smart grid of the future has got a different challenge. It is the supply becomes inflexible. We have no control over the energy we get from solar, neither we do have any control over the energy we get from wind. So supply becomes non-dispatchable, and therefore the demand has to change. And so we are going into an era where the demand is going to follow the supply. That is going to be the modern and future smart grid. So now here comes the relevance of smart grid in the future power grid. Because when the demand has to follow the supply, we have to imagine the extent of communication and information technology, information and communication technology, which has to be in place so that an AC connected or a washing machine or a pump connected in the home has to recognize that the power in the supply side has changed and he has to act accordingly. So such advanced is expected so that we can meet the expectation of load following the supply, demand following the supply. This is, in some common parlance, this is also called as demand response, and even in some context, we call it as demand side management or DSM. Yeah. So another great advantage which comes with this is that we are at present we have India especially suffers from a huge amount. But when we have our generation very close to our demand, when such an occasion arises, it actually reduces transmission and distribution losses to a huge extent. So we can probably, with the advent of the microgrids, the problem of T&D losses, high T&D losses, power theft, and all those problems might get solved along with the developments. So to summarize, power sector is shifting, generation is shifting from central to distributed. So a few more points related to before we close the renewable part. One more advantage which is there is, especially for India, is that the work required to produce the same amount of power, if it is one person, for example, for solar, as per the US Department of Energy, 79 people are required to produce the same amount of electric power. This is because of one of the advantage of solar, which is called its modularity. The same solar panel can be used as inside a room. It can be used inside a home. It can be used for an apartment. It can be used for a commercial establishment. And just increase the numbers, we can use it even at a megawatt utility scale. And at megawatt utility scale, the solar panel this opens up a wide scope for business models, because at utility scale they have to compete with coal prices and natural gas power plants and nuclear power plant rupees per kilowatt. Whereas at the residential scale, when rooftop solar comes up, when you do the cost benefit analysis, it need not compete with those rates. It can compete with a slightly higher rate of our telescopic tariff, which is there in most of our states. So each scenario becomes different, and therefore there arises different market models for which become enablers for solar energy proliferation in our country. And then we will have designers, we will have developers, we will have manufacturers, assemblers, installers, operation and maintenance team. A big crew will be there, and this will add a lot of jobs of our country, especially when our country is a youth, having a lot of a huge percentage of our countrymen are youth. So this is a great opportunity. Now I would wish to move forward to another special and peculiar fact. In fact, Germany was pioneers in rooftop installations, and they had actually installed around 45.9 gigawatts of solar PV by the end of 2018. And the amazing fact here is that 98% of this capacity is connected to the distribution grid. So which gives us some confidence, which gives us a lot of confidence when we go for rooftop solar in our country. A system will remain fine. the reliability will be there, distribution transformers will work fine, overloading, many challenges we are anticipating, but this is some good news for all of us. So this was one aspect of the present scenario, and there is another huge thing, that is energy storage. To share India amongst energy storage, battery energy storage system is becoming very popular, and it is not limited to our homes. It is in fact, the batteries are getting connected not only in some part of the world, but even in our country, in India. So even this is another good. Especially if you see many of the slides, you can see that Port Blair, Andaman, etc. So probably more. We have so much of installations here because these they want to do away with the costly diesel generators, and if they can operate with renewables and battery storage system, that has started showing profitability scenarios. So BESS, battery energy storage system, is already become a common thing in grid scale, and even not only in across the world, even in India, it is getting huge popularity in various power grids. Now, even our national electricity plan from the Ministry of Power, even they highlight the role of energy storage, not only for the renewable energy, addressing the renewable energy intermittency. They are envisaging that energy storage will have a lot of other functionalities along with solving the intermittency. One of this can help maintain grid security. Right? So this is what our national electricity plan highlights, and why the reason. So why all these things have come up, because like renewables, the levelized capital cost of our storage technology has come down. As you can see in the graph, it has got a significant reduction in the levelized capital cost. Levelized capital cost means dollars or rupees per kilowatt hour of the storage technology. Now, if you can see here, we have lithium-ion batteries, we have lead-acid batteries. Maybe in 2008, lead-acid battery was more economical, less levelized capital cost. But the crossover has already happened, and it is envisaged with that improvement in manufacturing and even the research. We can see that by 2023 and 2028, lithium-ion is going to play a major role. Their capital cost has come down quite drastically. So, which is another good news. So, it is really a good news, because the two interdependent technologies are evolving at the same time simultaneously. We have renewables whose levelized cost came down, and in renewables has a problem of intermittency. For that, we need energy storage, and here we see that the energy storage levelized cost also has come down. This is a great news. Now, the possibilities of a battery energy storage system has maybe actually taken, reaped its benefits already in different parts of the world. And one of this is the 100 megawatt and 129 megawatt hour capacity battery energy storage system installed in Hornsdale in southern Australia. This system was installed by the Tesla. It was installed by Tesla, and they are expecting to expand it by another 50 megawatt or 64.5 megawatt hour. And this facility in Hornsdale is the largest lithium-ion battery facility in the world, and it is the primary job that the battery is doing. It is giving grid support services. That is when there is supply demand mismatch, there are frequency fluctuations. The great advantage of energy storage is that compared to other sources where the ramp up rates are high, and you cannot use them for short time compensation. But lithium and any battery technology, they have this quick ramp up. So whenever there is an immediate deficit, they can supply so quickly. They are used for grid support services. Now, along with that, what is also happening is that these batteries in southern Australia, they're actually participating in electricity market. So what's happening there is, when there is a supply demand mismatch, when the supply is, let's say, surplus, the batteries are storing the electricity. when there is a supply deficit, when the cost is high, the batteries are giving it back to the grid and thus earning a lot of revenues. To understand, to maybe like to really appreciate the scale, this fact would help. When dispatching at peak output, the battery in Hornsdale provides enough electricity to power equivalent to 40 homes, which is really huge. Now, so this is what in Hornsdale, Australia. See another scenario in Moss Landing in California. Here, Australia, we had it was some 127 some megawatt capacity. Here it is it's around 5 times more. That's what they are planning. California is very famous and very popular for their very affirmative and positive renewable energy integration and reducing their motivation to reduce greenhouse emissions. In fact, California had set a goal. Even when US pulled out of climate summit, California continued to set very good benchmarks for renewable energy integration. In fact, they had set a goal of reaching 100% renewable energy by 2045, which is a difficult challenge. But so far the progress is good. They have their own challenges. But coming back to our topic, the installation of this 567 megawatt capacity, installation would become the largest battery energy storage system in the world. And we have these peaker stations, PEAKER. We have these peaker stations, which are like natural gas plants, especially in the one in the Moss Landing, as you can see in the figure. It's a peaker station. It is a natural gas station. When the peak demands are there, these plants are switched on. So they are in the very same place. They are about to install this 567 megawatt battery energy storage system, and it is designed to take over the Moss Landing power plant, and its role as peaker station. Now, we might wonder that why we want to install such high capacity at such high cost, right? So that question might arise. So let us look at some figures, some stats. When we look at the first graph, California, as we said before, is rich in renewables. If we can observe, in May the 7th, the energy curtailment for that one day was 8,367 megawatt hours in California. This is a huge number. So what they are visualizing is that if they have a storage capacity, the very 8,369 gets stored in the battery energy storage system, and it can be used at the time when the demand is high, and they can switch off the peaker stations. And in fact, there was another statistics on the right hand bottom, which says that the megawatt hour curtailed in California in April 2019 was, that is the shiny sunny days, was around 190,000 hour was curtailed in California. So this is a scale. But here there is a challenge. The challenge is that if you look at the second graph, it shows the March 7th the curtailment was high. But if you look at the subsequent days, there is many days there is hardly any curtailment. So which means when we install this battery energy storage system after investing a lot of money, there may be days when the energy storage system might remain idle. So that might be one of the challenges, especially during the winter. This might become a challenge because in summer we have surplus of energy. So we have a lot of energy to surplus is there. So we have a lot to store. But in the winter, the solar is just sufficient to even to meet the demand. So the batteries might remain relatively less utilized. So this is one of the challenge. So to another discussion, coming back to India, along with renewables and energy storage, thing which is happening, and this is a discussion going around in the scientific community. We thought that the war of the currents, which is AC versus DC, was over, but now there is significant discussions going on that DC is coming back in very as a huge competitor for AC. We all know the reasons. I don't want to elaborate too much onto that. But with renewables such as solar and wind and all, which is run on DC, and the most energy efficient equipments like LED and brushless DC motors, which hardly consumes even less than half the power of their AC counterparts, and all of our electronic devices, computers, and everything which primarily are DC powered. So when most of our demand is DC, and when our future supply is also DC, then that question naturally arises. Why do we have to convert again and again? And in fact, the IIT Madras research had actually proved that the DC microgrid can actually have a 50% reduction in the system cost, because we don't need an inverter. We can even have inverter-less UPS because you don't require any conversion battery. So we are going to have UPS without inverter, which is an interesting proposition. I have chosen this particular topic is because of significance of DC grids and DC microgrids, which is a big competitor in the future. And secondly, because this project has already been implemented in 9,000 homes in 11 states of India, where they powered off-grid solar of 125-watt microgrid. So this was based on an article which was published in IEEE Spectrum in 2017. So we have discussed the present scenario. We are clear about the advent of microgrids, and let us further go ahead that how a microgrid of the future, how it will look like, and what are its various functionalities. So, holders, we have our, as you can see in the figure, these are the various prospective stakeholders. Our conventional system of generation, distribution, and consumption, that hierarchy probably is going to be reshaped. The stakeholders are becoming. We have consumers, we have micro sources, we have distribution system operators, we have energy suppliers. Right now, KSEB is the energy supplier as well as the distribution system operator. The home may have electric vehicles. We may have controllable or shiftable load for for the demand to follow the supply. Utilities will have substation storage to manage their peak demand as the battery cost comes down. So these are the various stakeholders. And the future microgrid, when we envisage the future microgrid, it should be able to meet the expectations of all these stakeholders in a constructive way. Now, I just want to for 1 minute, I just want to share about microgrids and virtual power plants. There is this title called virtual power plant. I just wish to share that these two are actually two different terms, because, for example, let's take a virtual power plant. If there is a fleet of electric vehicles, and like Uber, if all those electric vehicles are integrated with information communication technology, are geographically located at far away and far different places, but together, when they participate at night 8 o'clock, when the demand is high, and when they decide, okay, let us participate and let us supply the energy which we have stored, and when they participate and when they do peak shaving, it is called as virtual power plant. But whereas a microgrid is totally different. Microgrid is like, it's like a set of homes. It's like a village. They are not geographically dispersed. They are geographically located in a single premise. So that's it. Therefore, even though virtual power plants are aggregated, it is a virtual aggregation. It is not a physical aggregation, because they are geographically located at different areas. So coming back, let us look at microgrid classification. We may have a doubt. Is a home a microgrid? Microgrid is a city a microgrid? How do we define a microgrid? So in fact, all of these are actually microgrids, depending on the scale. For example, just a home with its electric vehicle, with its micro source like solar, with its demand side management, and a controller inside, that home can be considered, that low voltage home can be considered as a microgrid. People call it nanogrid. Now, if we have multiple homes connected at a microgrid controller, each home having their individual micro resources. Yeah, even that, when centrally controlled at the level of LV, low voltage feeder, even they are microgrid. Or even when we consider an LV grid scale, where we have residential feeders, we have commercial feeders, we have rural feeders, we have wind parks, we have PV farms, we have hydro, we have combined heat and power. all this controlled from one location, let's say using a microgrid central controller, even that can be. So we can define the different scales. That's the idea I just wanted to convey. Now, once we got some understanding, a good kind of an understanding about microgrid. So this is our typical distribution system. We have our meters. We have our PV panels, flywheels, storage capacity, fuel cells, micro turbines, everything. And we have our energy supply company and their billing system. We have our distribution system operator and their distribution management system, which manages the energy flow between these sources, storage devices, and loads, and automatic meter reading. So these are the functionalities of DSO. And the storage energy supply company is primarily dealing with billing system. So this is our typical power distribution system. Microcontroller is going to be different. It is going to have MC. MC is the microgrid controller. At every load point, you will have a local microgrid controller. These microgrid controllers, or MC, they will interact with the microgrid central controller. They will give all the information to the local controllers, will all give all to the central controller. And in the central controller, the operations as well as distribution system operator both happens at the level of microgrid central controller. So few point to realize here, we have to anticipate this importance of this figure. In fact, when the microgrid controller interacts with MDCC, it means that there are, like, for example, in itself there are like 1, 2, 3, 4, 5, 6, 7, 8, 9, around 9 microgrid controllers interacting with microgrids. So we need an excellent information and communication technology to convey all this information to the central controller. In our conventional grid, there is no communication at all. Only a person, an electricity board person goes and checks the meter reading and comes back. There is no communication. There is no flow. There is no communication flow. But in the microgrid control, there is bi-directional communication, right? As well as, since the consumers are no longer consumers, as most of us know that the name is going to change, they are going to become producer and consumer. We are going to call them as prosumers. Since the consumers are becoming prosumers, communication, our power flow is also going to be bidirectional. So our entire infrastructure, power infrastructure, has to be designed to cater this requirement of bidirectional power flow as well as bidirectional communication flow with good cybersecurity. So they proceed. Now, let us look at other options. As we control all the homes, let us have a control station, and can we control it centrally? Or, as we have seen in the previous slide, can we give some amount of control to individual homes and then do some higher control at the other levels? Probably the answer to that question is actually depending on the application. We cannot have a definitive answer. But as a thumb rule, we can say that centralized control, all the sensor information from all the homes, from all the appliances, are going to, and all the micro sources and micro storage devices and loads are going to come at a central location. This is going to make two things very complicated. One is the communication becomes very complicated and costly. Second is the control with all these inputs is going to be very complex. So these are the challenges with centralized control. So better we can go for decentralized control, where, as we have seen in the previous slide, where individual consumer has some amount of control at his level, and certain high load forecasting, renewable energy forecasting, and security monitoring, all such higher level of control can be given to the DSO or ESCO. To summarize, how to choose whether we should go for centralized or decentralized. For example, when the distribution system operator such as KSEB operates the entire they have installed, it's a utility scale renewable, and the power lines are also theirs. In that case, it's a single owner, so we can go for centralized control. But when the individual homeowners, like a rooftop solar system, that many of the things that are coming up, there are multiple owners, there are multiple stakeholders. At that time, centralized decision, centralized control might be a little difficult. So because every owner will have his own priority, so it is better to have the control to be decentralized. Because a person might not want to do load shifting, it is his choice. So being a centralized control, we cannot just make him shift the load at his home. He may need it. So coming to the market participation, centralized control requires a lot of complicated algorithm. But when we implement decentralized control, the owner may very unlikely that even in market negotiations and all that, it is very unlikely that owner might use complex algorithms. So installation mostly in decentralized, it is plug and play, just fit it and use it, as we have a distributed generation right now. And another point is that since every owner makes decision based on his own personal interest, so the solution in terms of the economics and the cost optimization and all that, the solution will be a local optima in the case of a decentralized control, and the solution will be a global optima in the case of a centralized control. Global optima can be in terms of any objective. It can be your economics, it can be reliability, it can be efficiency, it can be any objective. So in terms of all the objectives, in centralized control, the great advantage is that the solution we have is optimal. Communication requirements are high in centralized, low in decentralized. So so on and so forth. Now this is the diagram showing the various hierarchies, how it will be. You can see figure A is centralized, where all the units are communicating to the controller. Figure 2, it is decentralized. Every unit has his own controller. The problem is they are not communicating to each other. Every person is facing his own decision. Distributed, figure C. Here you can see that they are communicating to neighbors, but it's better than the previous, but they are only communicating to their neighbors. But when we go for the last one, which is called hierarchical control, they have some local control, but all the information, the relevant informations are conveyed to the upper level controllers, and therefore we have a good visualization of the entire microgrid, and therefore our decisions are going to be optimal, and are so that is a great advantage of hierarchical system. And I just wish to share that hierarchical system is considered to be is the most popular microgrid control approach is at present. So this again, we have at present they have defined 3 levels, secondary and tertiary levels, and then there will be a global control where, for example, just local control will be about whether to switch on the dispatchable loads or not. Secondary control will be about active and reactive power flow. Global control might be about how to operate in island mode or not. About the interaction. Global control is about interaction of the microgrid with outside. It's like all market participation and all those things will come at global control. So that the local control or the home level, you don't have to really bother about market participation and all that. Yeah. Now coming to the objectives. So how do we say that, okay, I have to operate a microgrid in the best possible way? That is not sufficient. We have to quantitatively define what our objectives are. So we have technical objectives, we can have environmental objectives, and we have economic objectives, all the 3 together. Technical objectives may be like, we want to reduce the power loss, we want to improve the reliability, we want to maintain the grid voltage properly. Even in island mode, system should work stable. Environmental, when we do all this, we want to ensure that the greenhouse emissions are reduced year after year. And what are the economic objective? When we meet the technical objective and environmental objective, we have to ensure that the costs are minimized. We have reduced outage cost, reduced losses, reduced emission cost, reduced O&M cost, operation maintenance cost, etc. Now we might wonder that, okay, all these things, this can be work together. This is fine. We can keep this as a target and we can work together. But the challenge here is that we have many stakeholders and they have different personal interests, and there is some possibility that this interest of the stakeholders might be conflicting. For example, let's take the case of the distribution system operator. Yes, I might be very much interested in stable grid voltage, stable island mode operation. Whereas but the regulatory authority might be interested in greenhouse emissions. They want to maintain the greenhouse emissions constant. Whereas a consumer, he might not even be bothered about whether we are getting power from the fossil fuel based power plant or renewable based power plant. He just wants his reliability and his cost to minimize. So there are very good chances that the stakeholders might have conflicting objectives. So the microgrid control should eventually, with interaction and negotiation with the stakeholders, should define for that microgrid what is the best suited objective for that particular microgrid. So this is the one we have been defining. So there may be interdependency and conflict in the objectives. Let's try to look at, we spoke about primary, tertiary, secondary and tertiary control. What all functionalities, in fact, we have already discussed that, what all functionalities which each one might have. Market participation may be an upstream topic. Battery management may be a low stream topic. So battery management at the home need not be done at the upstream. Market participation in the upstream need not be done at the home level. So we will create this hierarchy based on the stakeholders scope. Microgrid control is not complete without demand side management, as we said in the few minutes ago about the demand following the supply. So I just wish to share, most of us are familiar with this. I just wish to share some 4 to 5 demand side management related terminologies. One is peak clipping. That is, when you do an initiative and your peak gets reduced. The second one is called as peak clipping is also popularly called as peak shaving. The second one is called as valley filling. Valley filling is when a water pump which we could have run in the peak hours, instead of that we are running in the early hours. So that is valley filling. Third one is load shifting, or an easy to understand terminology will be peak shaving and valley filling. So you shift the load from the peak and put it in the valley. So an electric vehicle is an ideal example for that. You charge it during the peak hours, and you discharge during the peak hours. You charge during the off-peak hours. Then D is the another load conservation. When you implement energy efficiency initiatives, your overall load is going to come down. But at times when we add some equipments, our load might get built. So that's it. Now let's just quickly look at, now that we have understood the control, how to control, how to hierarchically control a microgrid. Now we need the negotiation to happen between the various stakeholders, and the next stage is actually to define a well-suited microgrid market model for that particular microgrid in that particular location. Every microgrid, there is no standard market model. It depends upon the geography. It depends upon the available renewable energy sources. It depends upon the political scenario in those places. It depends upon the guidelines and regulations of the land. Even it depends upon the financial health of the financial capability of the prosecutors. So with that, the model keeps changing. But I would just wish to share a few of those. One is DSO monopoly model. It's like the DSO owns the energy supply. The DSO owns the energy distribution system also. So since they are the one who generates, since they are the one like KSEB as of now, they're the one who distribute also. So that model, with the popular model, is called as DSO monopoly model, where let's say KSEB will have, or the state electricity board will have utility scale solar panels, and already they have the infrastructure, so they will the consumers just have to buy it as it was before. But only difference is that it is not centralized. Free market model is totally free. Every stakeholder can make any decision which he finds comfortable, and they will negotiate. All of them will come at one platform: energy supplier, demand distribution system operator, prosumer, everyone will come at one single place and they will negotiate and they will terms of the business and they will start the operation. Then there is this another model called as a prosumer consortium model. In this model, the prosumer and all the prosumers association, all the prosumers come together and they will have this functioning body called as prosumer consortium. So it is this consortium which is going to take most of the decisions related to, for example, once they become a consortium, they may interact with the market, right? So when they interact with the market, what price should we buy power? When we sell power, the consortium together will decide at what price they should sell power. For example, in KSEB as of now, it's like, if I remember correctly, rooftop solar power is sold at around 2.94 rupees, and power we purchase, maybe it's a telescopic billing, but nevertheless it is definitely more than that. So, but then in the net metering scheme, the supply and demand, the net is calculated. So it's calculated at the same rate. So that 2.94 is only for the surplus power. Well, the idea I wanted to share was that prosumer consortium will make negotiations and decisions. So these are various market models. So coming to our last topic, which is multi-microgrid. All these microgrids, I'm just going to zoom out a little bit more. All these microgrids will have their best possible operations. I would wish to call it as another local optimum. If those two microgrids, if they had interacted together, if they had shared their resources, probably we could have had a better optimal operation. So that is where the idea of multi-microgrid is coming. So multi-microgrid gains its importance because of the benefits of interconnecting two microgrids. We just wish to start. In fact, even our grid had reaped and harvested the benefits of interconnectedness. 1960s, we were having individual state grids were connected to form regional grids. During the 90s and the 2000s, we started integrating the regional grids. And in 2013, with the southern grid getting interconnected, we became one nation, one grid, and with one frequency. So our integration became complete. Now, the benefits are we have this power corridors and we have so much of diversity in our generation and even in our demand. So when there is a deficit in supply in one of the regions, instead of building a new power plant, now we have this transmission corridors which are connected. We can get the necessary power from the nearby region, and thereby we can we need not install new power plants. So such are the huge benefits. So a lot of economy, lesser generation capacity, power transfer becomes economical. We all know this. Now, to borrow idea, and I want to express in terms of the microgrid context. This interconnection will start appearing not only has appeared in the main power grid, it will also start appearing in the distributed generation. Individual homes, or sometimes it is called as nanogrids, they come together, get interconnected. Let's say a village or an apartment. So they come together and they'll form microgrids, and microgrids gets interconnected, and they will form microgrid clusters or multi-microgrids or interconnected microgrids. There are different terms they use for that. Now, they are going to be dispersed over a wide geographical area. We need the help of smart grids. It has to be facilitated with information and communication technology. We need advanced metering infrastructure to collect all the data reliably, and it has to be monitored and controlled by a very smart multi-microgrid controller. So the microgrid of the future is basically the fundamental building block of our future smart grid. And for example, just to explain the benefit, probably I'll just skip this slide. Okay, just to explain, for example, when instead of having an energy storage at each home, if we have a centralized energy storage, we can exploit the benefits of diversity factor, and thus the installed capacity can be much less than the sum of installed capacities which would otherwise have been at individual household batteries. So this is the benefit of interconnection, and this benefit can actually be harnessed and harvested not only for the same logic applies for community solar or any micro resource for that matter. We can harvest the benefit of interconnection. Yeah. So the challenges in main microgrid benefit of as interconnection increases, system becomes complex, secure operation becomes a challenge, control functionality increases, sensors increases, data increases. We need fast processing of large quantity of data. Big data analytics will come into picture. Multi-microgrid control needs to handle complex, very complex system requirements. Thus, we need a smart multi-microgrid control. Finally, I would wish to conclude with just a brief idea about multi-microgrid. So we already know that the microgrid central control will be there, and then we will have a central autonomous controller, and which will integrate all the microgrid central controllers. And there had been research papers published about how this central autonomous controller should be, and they continue to, most of the researchers, they continue to propose again the same hierarchical structure which was followed in the microgrid level for the multi-microgrid as well, but the functionalities might be very different. Now, to conclude, this is the last slide. So to conclude, this is the roadmap for microgrid evolution. The status quo, in 2010, micro sources, we had we have connected some solar panels. In fact, Kerala was very aggressive and alert with its lot of off-grid solar panels. We connected many micro sources into the grid. We followed a fit and forget philosophy towards microgrid management. But during the next decade, that is 2010 to 20, we saw a boom of micro sources. Huge amount of commercial, industrial, as well as residential micro sources were started being implemented in 2010 to 20. And even the battery storage cost came, as we have seen before, it started coming down drastically. This was also motivated by the climate change motivation and the Paris Climate Summit, which led to the proliferation of microsources. And what we can see in the future, how will the evolution be in the future? So as of now, we do not have any local markets. So, so there may be liberalization of the market. So we will start having local markets, and micro sources penetration will continue to increase. So 2020 to 2030, we can expect a liberalization of or creation of local markets. Like we have market for vegetables, we may have local markets for renewables or energy. And eventually, as the technology further progresses, let's say 2030 to 40, the communication and and information technology will become cost economic, and smart metering will become a part of our everyday life. Energy storage costs will further go down. So we will have an extremely intelligent microgrid control, which is going to come up in the coming future. Let's say 2032. 2040. So intelligence, along with the market, intelligence is going to come. Automated intelligence is coming in the near future. Thank you very patient listening for the past 1 hour. I hope some valuable informations are conveyed. Thank you.
Okay, thank you, sir. We haven't received any questions chat window. So if any of the participants want to ask any questions, they can unmute their button and ask the questions. Post the questions, sir. Hello. Hello, Kirtana. You had. If you have any doubt, please pose the question. So there is one question posted. Can we call this as multi-microgrid, as smart grid? Are both the same?
That is a good question. It is envisaged that microgrid gets interconnected to form multi-microgrids, and what we call as our regional grid, they would probably still be there. But a regional grid will be a combination of multi-microgrids. So then all those regional grids will get integrated together. We will still continue to have our conventional base load plans, probably are owing to the intermittency of renewables. We will continue to have our nuclear plants and all that. To specifically answer that question, so this multi-microgrids with its advanced information and communication facility is going to be called as the future smart.
Is it possible to interconnect a smart grid for a selected area with another conventional grid for balance area?
It is very much possible because let's say conventional grid means we will have our conventional generations, centralized generations such as hydro, nuclear power plants and all that. So it is not going to be a it's not going to be a jump from conventional to conventional grid to the distributed grid. It is going to be a healthy and mutually complementing transition. In fact, for the microgrid transition, which or the distributed generation transition, the support of the conventional grid is required. So the answer is, I believe that definitely they can and they will operate together for a very long time and supporting each other and complementing each other.
Can you give some? Yeah. Please, please.
Yeah, you had proposed a roadmap for the microgrids and the multi-microgrids. Is it for India or for the world? This thing, global scenario. This roadmap.
This actually this is for general as world as such. Yeah.
That's okay. So we are still in the nascent stage. We have we have not, though we have reached 2020. We have not reached a microgrid level, though we have rooftop solars and other solar installations coming up in pockets. It's not like it has become a general trend, or it's just in a few pockets only. So how do you see this to come up in 2020 as a local market? Still, it has not become a market. The commercial aspects have not worked out really well now.
Okay. Yeah, that's right. But I believe that there are very at the level of planning, there are discussions which are going on where, in fact, in Mumbai, if I remember correctly, Tata and Adani are actually giving power to the consumers. They are also a part of the, they are also, so local market and local players are expected in the future. But I do not have a significant knowledge about the market structure and their envisaged future, to be frank.
Okay, thank you.
There's a question from Kirtana PB. She is asking whether both smart grid and automatic energy grids have the same meaning.
Yeah, smart grid and automatic energy grid. Automatic energy grid, automation is one of the functionality or feature of smart grid. So in that sense, automatic grid and smart grid are similar. In fact, automatic grid can be considered as a subset of smart grid.
Okay, thank you, sir.
Thank you.
Do we have more questions? If anyone want to ask, please unmute their button. We had received some questions. So can multi-grids completely replace conventional grids in the future?
It depends, okay, at present, that as of now, multi-grids or multi-microgrids basically relies on distributed generation and on renewables, right? So renewables are having this, the fundamental challenge of renewables is intermittency. So energy storage technology is considered, as we have seen in this one of the slides, like how much of curtailment is happening in California. So energy storage is considered to be one of the solution for intermittency, but still that seems to be a very costly proposition. And in fact, the latest research what they are speaking is that they are looking for some very long-term energy storage, such as something which we can store in June, July, in summer, we can store it and then we can use in winter. So if something like that comes up, this combination of renewables and energy storage becomes a success, then it is the world of renewables. But till then, till that breakthrough, we don't know when that breakthrough will happen. But till that breakthrough, conventionals are here to stay. There is no doubt about that.
Yes, Mr. Anu, can I ask a question? It's not a question. Can I intervene? Kuriakos here.
Yes, sir. Yes, sir.
Okay, Mr. Anu, if I'm right, 2030 is the target for implementing the smart grid in India. And I think Mr. Dr. is the head of the, I don't know, right now who is the person, I don't know. By 2030, we are supposed to implement smart grid all over India.
Okay.
And and they were in the process of making a IS standard for this or a protocol.
Okay.
Do you have any idea about what is the present status of the present protocol and the IS standard for? They were working on that, and now I don't know. Really, don't know.
Okay, sir.
Situation. That is question number one. Question number two is they were also, that is open to everybody for the discussion. Once if the smart grid comes in a picture, definitely some supply has to be disconnected or some load shedding has to be implemented immediately. Like suppose it's a full sun and all the solar panels are working and suddenly the sun goes out. So naturally there will be a sudden throw off of generation, and naturally the conventional generating stations has to be switched on, and meanwhile there will be some point when which there will be a dip in the generation and a rise in the consumption. At that point, the smart grid operator or the switch off the load points. So there will be a tariff differentiation. Those who opt for the switching of the live power load, they'll be given a different kind of tariff, or subsidized tariff, because without your knowledge, your power is going to be switched off because of the throwing of the generating stations. Even there was a discussion going on. I don't know present status. Do you? These are the two questions. Do you have any idea about this? I mean.
Okay, sir. Sir, about the standard, I have not explored much, sir. Coming to the second question, like that sudden shifting in load. So the challenge is that the existing generation systems might not be able to ramp up at the rate that is necessary, so that we can maintain the supply demand balance, or we can maintain the frequency within the limit. So as what is being done in Hornsdale in Australia, they have installed the energy storage system. So since energy storage system cost is coming down drastically and is expected to come down even down further, we may be able to see more of energy storage. And even when electric vehicles are going to proliferate probably in the next 10, 15, 20 years. So the energy storage spinning wheel is spinning reserve is going to play a major role. And why they are going to play a major role? Because they will start supplying power back instantaneously. So their power electronic controllers are such that the moment they sense a change in the frequency, they will start responding instantaneously. This is from energy storage point of view. And another is
that is within 100 milliseconds. It has to take care of it.
Okay,
am I right? It is within milliseconds. You can say 100 to 150 millisecond. It has to take. Right?
Okay, fine.
Maybe. I don't know whether I don't know the technology right.
Okay.
Now.
What I'm aware of is in Australia they are using it for frequency regulation for that disturbances, but up to what precision or up to what resolution of time is something to be explored. And second thing, as you said about demand, in many of the countries, and in fact in US, in California itself, there are many discoms. In many discoms, they have different tariff structure, they have different tariff policies, etc., etc. So the distribution system operator has this freedom to make an agreement with the consumer, as you have said, sir.
Yes, exactly. Exactly.
Yeah. So and participate in the demand response.
Okay, then one more point that is to be discussed at this point of junction is when you install, when you go for the smart grid, the whole meters also has to be changed, smart meters.
That's right.
When the meter has to, the command is given to the meter, and meter has to switch off the power load or the light load. Got the point? I mean, when the generation goes off, the power point, like in European countries, they have what do you call heating load, and what they call is heating load. This distribution company has got the right. They have to make an agreement with the consumers, and they'll switch off the power load first. So that the command is given to the meter, and the meter has got a feature in which it will bifurcate. It has the wiring is done in such a way that it has been bifurcated, the power load and the light load. So I think also we have to do the same thing. We have to have a meter which is capable of receiving this command also. Okay.
That's right, sir. Yes, sir. That's right, sir. Very true.
Okay. Thank you.
Thank you, sir.
I think we can close the QA session here. I invite Anil sir to express the vote of thanks.
Good evening.
Anil, yeah, thank you, sir.
Good evening, I'm Anil. Er.Anu Kumar is one of my friends at Amrita Vishwavidyapeetham. He works there as assistant professor in the EEE department of Amrita School of Engineering at Timadai campus. He has made a nice presentation on the state-of-the-art power system, power grid scenario. And it's mostly in the research stages. The implementation is mostly in the research stages. And Engineer Anu, I take this opportunity to extend you hearty thanks for your presentation. And lastly, I thank all the participants of this webinar. In fact, the participants are the persons who make the webinar a success. Thank you all. Thank you very much.
Yes.
Okay, thank you, Anil sir. I think we have come to the end of the session. Thank you, Anuji sir. And thank you all the participants for joining the webinar series.